LangChain Elasticsearch Client. Create Elasticsearch Client Summary. Creates Elasticsearch Client for LangChain to interact with Elasticsearch Index. Inputs: the address of the Elasticsearch server where LangChain will connect. For instance, if you have an Elasticsearch instance running on your local machine at port 9200, the URL would be http://localhost 9200. Credentials required to authenticate with the Elasticsearch server. These could include a username and password or an API key, depending on how your Elasticsearch instance is configured. Outputs: an Elasticsearch client object that LangChain can use to interact with the Elasticsearch index. This client allows you to perform operations like searching, indexing, and updating documents in the index. Steps: the process begins by initializing a basic Elasticsearch client object. This object provides the fundamental structure for interacting with Elasticsearch. The Elasticsearch client is configured with the URL of the Elasticsearch server. This establishes the connection point for LangChain to communicate with the server. The Elasticsearch client is further configured with the authentication credentials needed to access the Elasticsearch server. This ensures that LangChain can successfully authenticate and interact with the server. Prerequisites: the Elasticsearch server must be up and running. This ensures that LangChain can connect to the server and perform the necessary operations. This is the address used by Elasticsearch to communicate with other systems. The format is typically hostname port. For instance, localhost 9200 indicates a server running on your local machine at port 9200. An Elasticsearch index, which is a collection of documents, must be created. This index acts as the storage location for the data that LangChain will work with. My index is a placeholder name for an actual Elasticsearch index. You would replace this with the name of the index that you have created in your Elasticsearch instance. Fine-tune parameters: the specific Elasticsearch index that the LangChain client will interact with. This allows you to target a specific set of documents within your Elasticsearch instance. The version of the Elasticsearch application programming interface API that the LangChain client will use to communicate with the server. Choosing the correct API version ensures compatibility between LangChain and your Elasticsearch. Setup: challenges and fixes. An incorrect Elasticsearch URL can prevent LangChain from connecting to the server. This issue might arise from typos in the URL, incorrect port numbers, or an Elasticsearch server that is not running. Double-check the URL to make sure it accurately reflects the address of your Elasticsearch server. Also, ensure that the Elasticsearch server is running and accessible. If necessary, restart the Elasticsearch server or the LangChain client to apply the changes. Invalid authentication credentials can block LangChain from accessing the Elasticsearch server. This problem can occur if the provided username, password, or API key is incorrect, or if the credentials are not properly configured in the Elasticsearch server. Review your authentication credentials to ensure they are correct and match the settings of your Elasticsearch instance. You might need to verify that the credentials are associated with the correct user account or API key in the Elasticsearch server. Once you have confirmed the credentials, restart the LangChain client to apply the updated information. If the specified index does not exist in the Elasticsearch server, LangChain will not be able to interact with it. This issue may occur if the index name is misspelled, the index was accidentally deleted, or the index was never created. Make sure the index name is correctly spelled and that the index actually exists in your Elasticsearch instance. If necessary, create the index using the Elasticsearch API or a tool like Kibana. Once the index is created, restart the langchain client to establish the connection. If Elasticsearch is not accessible, langchain will fail to connect to the server. This issue might arise due to network problems, firewall restrictions, or an Elasticsearch server that is not running. Verify that the Elasticsearch server is running and that your network configuration allows access to the server. Check for any firewalls or network settings that might be blocking the connection. You might also need to investigate the Elasticsearch server's logs for potential errors. Langchain Elasticsearch Vector Stores. Elasticsearch Store, a base class for retrieval strategies that use Elasticsearch. Elasticsearch is a search and analytics engine that enables full-text search, structured search, and analytics. This base class provides the foundation for retrieval strategies that leverage Elasticsearch's capabilities to retrieve relevant documents based on queries or vectors. Inputs: query: the text-based query used to retrieve documents. This could be a user-entered question, a keyword search, or a complex query string. Vector: a numerical representation of the query, used for semantic search. Vectors capture the meaning of the query, allowing retrieval of documents that are semantically similar even if they don't contain the exact words. Outputs: a list of documents that match the query or vector. This list represents the documents that the retrieval strategy deems most relevant to the provided input. Steps: 1. Generate a query or vector. This step involves transforming the input query or vector into a form suitable for Elasticsearch. It could involve processing the query, embedding it into a vector, or constructing a search query string. 2. Retrieve documents from the Elasticsearch index using the query or vector. This step uses Elasticsearch's API to execute a search based on the generated query or vector. It returns a list of documents ranked by their relevance to the query or similarity to the vector. Prerequisites: an Elasticsearch index with documents that are relevant to the query or vector. Elasticsearch requires a prepopulated index to perform searches. The index must contain documents related to the query or vector in order to retrieve relevant results. A real-world example could be an index containing articles about a specific topic. A vector store that has been initialized with the Elasticsearch index. This ensures that the retrieval strategy can access the Elasticsearch index and retrieve documents. This vector store should contain the data from the index in a format that the strategy can work with. This can be achieved using libraries that allow you to connect Elasticsearch to a vector store. Fine-tune parameters. K. The number of documents to retrieve. This parameter controls how many documents are returned in the final output. Setting a higher value retrieves more documents, which could include less relevant ones. A lower value provides a more focused set of results. Similarity metric. The similarity metric to use for retrieval. This parameter defines the method used to calculate how similar documents are to the query or vector. Common options include cosine similarity, Euclidean distance, or Jacquard similarity, each with different strengths and weaknesses. Choosing the right metric depends on the nature of the data and the desired level of semantic similarity. Challenges and fixes. The query or vector may not be effective at retrieving relevant documents. A poorly formulated query or vector may not accurately capture the user's intent. This can lead to retrieval of irrelevant documents. Possible solutions include refining the query or vector using techniques like query expansion, keyword stemming, or stop word removal. The Elasticsearch index may not contain all the relevant documents. Incomplete indexes can result in missing relevant documents. Ensuring that the index is up to date and comprehensive is crucial for retrieving all relevant documents. Consider regularly updating the index with new data and exploring methods for expanding the index coverage. Langchain Elasticsearch vector stores approximate retrieval strategy. This strategy leverages the power of approximate nearest neighbor and search within Elasticsearch to retrieve documents that are semantically similar to a given query. It's a core component of information retrieval systems, allowing for efficient and effective document discovery based on their content meaning, rather than just exact keyword matches. Inputs: a numerical representation of the query, generated by an embedding model, capturing the semantic meaning of the query text. The Elasticsearch index containing the documents to search. This index is prepopulated with document vectors, also generated by an embedding model, representing the meaning of each document. Outputs: a list of documents ranked by their similarity to the query vector, providing the most relevant documents based on their semantic content. Steps: the query is transformed into a numerical vector using an embedding model, allowing the system to understand the meaning of the query. The query vector is then used to search the Elasticsearch index, specifically utilizing the AND search capabilities. This means finding documents with similar vector representations to the query vector, even if they don't share exact keywords. Based on the results of the AND search, the documents with the closest vector representations are retrieved, providing a ranked list of the most relevant documents. Prerequisites: the Elasticsearch index must be configured for vector search. This involves creating a dedicated field for storing the document vectors and specifying a appropriate data type for vector storage, allowing for efficient vector-based similarity calculations. This typically involves configuring Elasticsearch to support vector data types, such as dense vectors using the dense vector data type, and setting up an appropriate index structure for efficient vector search operations. For example, HNSW hierarchical navigable small world index is often a good choice for vector search. Fine-tune parameters: the number of nearest neighbors to retrieve during the search process, controlling the breadth of the search results. The field within the Elasticsearch index that contains the vectors representing each document, ensuring that the search is performed against the intended vector field. Challenges and fixes: the search process can be latency intensive, particularly in large-scale indexes with many documents. Optimizing the Elasticsearch index configuration can significantly improve search performance. This might involve adjusting the number of shards and replicas, optimizing the index structure, and leveraging techniques like caching to reduce latency during search operations. The retrieved documents may not always fully capture all relevant information, potentially missing important documents that are semantically similar but have slightly different vector representations. Fine-tuning the embedding model used to generate the query and document vectors can improve the accuracy of the search. This might involve choosing a more suitable embedding model for the specific domain or task, adjusting the embedding model's hyperparameters, or incorporating domain-specific knowledge into the embedding process. Additionally, optimizing the search parameters, such as the number of nearest neighbors retrieved and the similarity metric used, can help improve recall and ensure that the most relevant documents are returned. Langchain XOR tools XOR find similar results. A comprehensive description of the XOR find similar results tool, outlining its purpose, inputs, outputs, steps, prerequisites, fine-tune parameters, and potential challenges with respective fixes. Tool name: XOR find similar results. Tool description: This tool is designed to retrieve similar results to a given query from a specified ExaSearch index. It leverages the power of ExaSearch's indexing and search capabilities to provide relevant and accurate results. Inputs: index name description, the name assigned to the ExaSearch index containing the data relevant to the search query. Example: world geography. Outputs: results description, a list of results deemed similar to the input query based on the selected similarity metric. Example: a list of documents or web pages containing information about the capital of France. Steps. Step 1: description. The tool initiates a search query to the ExaSearch index using the provided query. Step 2: description. The tool retrieves the top similar results from the index based on the defined similarity metric and top K parameter. Step 3: description. The tool returns the retrieved list of results to the user. Prerequisites: ExaSearch API credentials. Description: access credentials for the ExaSearch application programming interface API to enable the tool to interact with the ExaSearch index. Fine-tune parameters. Similarity metric description: the metric used to assess the similarity between the query and the indexed data. Example: cosine similarity, Jacquard similarity, or TF-IDF. Challenges and fixes. Challenge 2: description. The tool lacks the necessary access credentials to interact with the ExaSearch application programming interface API. Fixes to challenge 2: provide API credentials. Description: provide the appropriate API keys or tokens to the tool, granting it the necessary permissions to interact with the ExaSearch index. Langchain ExaTools ExaSearch Results Summary. This is a description of the ExaSearch Results Summary tool used in langchain. The tool facilitates retrieving documents based on a user's query from an Exa knowledge base. Inputs. Query represents the user's search request. This can be any natural language question or phrase that the user wants to use to find relevant documents. For example, a user might search, what are the key benefits of using cloud computing? Index name refers to the specific index within the Exa knowledge base that the tool should search. Indexes are used to organize documents within the knowledge base. They allow for more efficient and targeted searches. Outputs. Search results. The output of the tool is a set of documents that are deemed relevant to the user's query, based on the search algorithm and the index being searched. The results are usually ranked based on their relevance to the query, with the most relevant documents appearing first. Steps. Connect to Exa knowledge base. This step involves establishing a connection to the Exa knowledge base. This is typically achieved through the Exa application programming interface API. Execute search query. Once connected to the Exa knowledge base, the tool uses the user's query to initiate the search within the specified index. This step involves sending the query to the Exa API for processing. Return results after the search is executed. The Exa API returns the results. These results will be a set of documents that match the user's query, ranked based on their relevance. The tool then presents these results to the user. Prerequisites. Exa knowledge base. This is a requirement for using the tool. The Exa knowledge base is a collection of documents and data that have been indexed for efficient search and retrieval. It acts as the foundation for the tool's functionality. For example, a business might use Exa knowledge base to store and search through customer data, product specifications, or technical documentation. Exa API key. The Exa API key is a unique identifier that enables access to the Exa knowledge base and its search functionality. It is used to authenticate requests and ensure secure communication. It can be obtained by signing up for an Exa account. Fine-tune parameters. Maximum number of results. This parameter allows users to specify the maximum number of documents they want the tool to return. This can be helpful for limiting the number of results displayed to the user, especially when dealing with large knowledge bases. For instance, a user may only want to see the top 10 most relevant results. Ranking algorithm. To use the tool uses algorithms to determine the relevance of documents to the user's query. These algorithms are designed to provide the most relevant results first. Users can often fine-tune the ranking algorithm used by the tool, allowing them to tailor the search results based on their specific needs. For example, a user may want to prioritize results based on document freshness, relevance to specific keywords, or other criteria. Challenges and fixes. Incorrect XRP key. If the user provides an incorrect XRP key, the tool will not be able to connect to the XR knowledge base and retrieve results. To fix this, ensure the API key is correct and has been entered accurately. A user can verify their XR API key on their XR account. Index name not found. If the index name specified by the user does not exist within the XR knowledge base, the tool will not be able to retrieve any relevant documents. To fix this, check the index name carefully. Make sure it is spelled correctly and exists in the XR knowledge base. This can be done by examining the list of available indexes in the XR user interface or by consulting XR documentation.